In this lecture, we're going to justify the conditions that we stated earlier. Now, remember that the Haber process is a reversible reaction, so we need to apply our understanding of the Chatelier principle. So we're going to bring in the Chatelier principle and try and justify the conditions that we're using. Now, the temperature that was stated in the conditions that we discussed for the Haber process is 450 degrees centigrade. So 450 degrees centigrade is the temperature that is used in the Haber process. Now, this is a very important topic, and the first thing that they ask is why don't we use? So the first question that is going to be asked is uh, why isn't the temperature greater than 450 degrees centigrade? Why are we not using a higher temperature? So let's look at the reaction, and let's say if I increase temperature, then according to Le Chatelier's principle, according to Le Chatelier's principle, it's going to counter that. It's going to try and equilibrium would tries to decrease temperature. So equilibrium is going to try and do the opposite. It's going to try to decrease temperature. And temperature is decreased if the endothermic reaction is favored. So the endothermic reaction, which in our case, since the enthalpy is it is negative, which means that the forward reaction is exothermic. So our backward reaction would then be endothermic. So the endothermic reaction is favored, which means that the backward reaction would be favored. And we don't want the backward reaction to be favored. We want the forward reaction to speed up. So it's not really going to help us. The yield of ammonia, or the output of ammonia, is going to decrease. So the yield of NH3 decreases since the equilibrium is going to shift to the left hand side. This is the reason why we do not increase the temperature. Vice versa. The same can be said about the other statement that can be made in this case is, and that statement is, why are we not using a lesser temperature, less than 450 degrees centigrade? Now the opposite is going to happen if we decrease temperature. So if we decrease temperature, equilibrium would try to increase temperature. It's going to counter that change, according to Le Chatelier's principle. So the equilibrium tries to increase temperature, which in our case, if we want to increase temperature, exothermic reaction would be favored, which in the above case, if we go back to the reaction that we are studying, exothermic reaction is the forward reaction. So which is a good thing. Exothermic reaction would be favored. Exothermic is the forward reaction. So the forward reaction would be favored. So forward reaction is favored. And the yield would increase. Yield of NH3 would definitely increase, which is a good thing. So our yield increases, which means that the output increases. So what's the problem here? Why are we not decreasing temperature? We're going to go into that detail now. So the reason why we're not decreasing temperature, and let me just 1 second. Now that's a good thing. Now the reason why we're not decreasing temperature, that has to do with the rate of reaction. When we did one video lecture on the rate of reaction, the confusion between equilibrium and the rate of reaction. So whenever we decrease temperature, whenever we're going to do that, the rate of the reaction is going to decrease. So the rate of reaction decreases, the reaction slows down. Although you're getting more NH3, you're getting more output of NH3, but it's going to take a longer time. Let's say first, initially you were getting 20% ammonia, but you were getting it in, let's say, 1 hour. Now you'll be getting 80% ammonia, but you'll be getting it after 7 days. So the rate of reaction is important. You want the process to be very fast. It's better that you get a smaller amount, but if you get it in a quicker time, then it is beneficial. So the rate of reaction decreases, and so it's not going to be beneficial. So this is the reason why we do not decrease temperature. If we decrease temperature, although yield of NH3 increases, but our rate of reaction decreases. So the equilibrium takes a longer time. Equilibrium takes a longer time to produce NH3. We also need to justify the conditions for pressure used, and the pressure that we that the Haber process uses is somewhere between 200 and 1000 atmospheres. So atmospheric pressures. So that's the pressure that is used in the Haber process. You can write down 200 to 1000 atmosphere in your exams. Now we need to justify why not a higher or a lower pressure is used. Why isn't the pressure greater than, let's say, why isn't the pressure higher? So why is not a, so let's discuss the first thing, and we need to bring in the Chatelier principle, and we will relate this to the Lee Chatelier principle. So what are the problems faced when a higher pressure is used? So that's our first statement that we will justify. Now, if you look at the reaction, if you increase pressure, we will bring in and discuss the Lee Chatelier principle. If we increase pressure, the equilibrium tries to decrease pressure. So equilibrium is going to do the opposite. If you increase pressure, the equilibrium will try to decrease pressure. If I'm using a higher pressure, it means basically I'm compressing my system. So the only way the equilibrium will try to decrease pressure is if it favors the side with the lesser volume. So the side with the lesser volume would be favored. So it favors the side with lesser volume. We are compressing it, the volume is compressed, there is lesser volume now. So the side which occupies lesser volume, that side would be favored. So if you look at the reaction, your left hand side has a total of 4 moles, whereas your right hand side has a total of 2 moles. So your right hand side would occupy a lesser volume, whereas your left hand side would occupy a larger volume. So we can now state that the side with the lesser volume, that side is the right hand side. So more ammonia would be produced. More NH3 is produced. More NH3 is produced, which is a good thing. Your yield increases. Our output increases, which is also a good thing. So, what's wrong with using a higher pressure? Now, what's wrong with using a higher pressure is there are a few things which are wrong about using a higher pressure. One of that is that a higher pressure would increase the cost. It would increase cost. Your plant is going to be more expensive. So it would increase cost. More expensive plant has to be made because if you're using higher pressures, your pipes, etc., would need to be very thick. So they would, to reduce the chance of an explosion, there would be chances of explosion of using it. Wouldn't be very safe. So high pressure is not recommended. So it's better to reduce cost, and to for safety reasons, it's better to use lower pressures. So that's one of the problems of using a higher pressure. A higher pressure is therefore not used. Now the other statement is, uh, why are we not using a lower pressure? So what's wrong with using a lower pressure? So it's going to be the opposite. We've already discussed, so we can do the opposite. If you use a lower pressure, equilibrium would try to do the opposite. The Le-Chatelier principle is going to try and counter that. So the equilibrium would try to increase pressure. And the only way it can do that is by favoring the side which occupies the larger volume. So it's going to favor the side. So it's going to favor the side with larger volume. Now we know that side is the left hand side. So your yield is going to decrease. We already discussed that the left hand side or the reactant side has 4 moles, whereas the product side has 2 moles. So the larger volume side would be the reactant side. So more reactants would be produced. Would be produced, and your yield would decrease. So your yield decreases, which is why we would not be using lower pressures, because lower pressure would favor the left hand side. The backward reaction would speed up. Now, the last condition that we need to justify is the use of a catalyst. So, iron is used as a catalyst in the Haber process. And what's the purpose of a catalyst? Now, justifying this is very simple. A catalyst, it reduces the activation energy. So, a catalyst reduces the activation energy and speeds up the reaction. It speeds up the reaction. So we can say that indirectly it is going to be more economical. It's going to be more economical if we use a catalyst, because a catalyst would reduce the energy requirements and it would give you a faster reaction. The last thing that we need to justify is that NH3 is constantly cooled and condensed, and it is constantly removed. Now, if you remember the Le-Chatelier principle, that if I remove or reduce the concentration of, let's say I reduce the concentration of NH3, and I'm going to write that in square brackets. So if I reduce the concentration of NH3, the Lee-Chatelier principle states that the equilibrium tries to increase the concentration of NH3. So since we want more NH3, the forward reaction would be favored. Forward reaction would be favored, and your yield would, or output of NH3 would increase. So your yield increases. So if I remove NH3, more NH3 would be produced at a faster rate. So constantly cooling and condensing the NH3 and removing it from the reaction mixture would help us to improve the yield of our reaction.